Hello everybody, welcome to our lesson. Today's topic is motional EMF. This is the goal of the lesson. At the end of the lesson, you'll be able to calculate EMF due to the motion of a conductor in a magnetic field. In previous lessons, we have defined the induced EMF as an EMF produced by the change in magnetic field. And the interesting thing is that even if there is no change in magnetic field, there are ways of inducing EMF. In this lesson, we will describe the method of inducing EMF by moving a conductor inside a stationary magnetic field. And yes, it is observed that if a conductor is moved through a constant magnetic field, at the ends of the conductor, potential difference is produced. Hence, an EMF is induced. The method of inducing EMF by moving a conducting rod in a uniform magnetic field is called motional EMF. This special case of electromagnetic induction arises as a result of the magnetic force that acts on a moving charge. There are many electrons inside a conductor which are moving freely from the atoms, and under the influence of this magnetic field, these mobile electrons will move to the lower end of the conductor, leaving behind an equal amount of charge at the upper end. And these charges feels two types of force: magnetic force from the magnetic field and the electric force from the induced electric field. The charges accumulate until the electric force exerted on each charge is balanced by the magnetic force. And by balancing forces, we can find the magnitude of the electric field. So, the electric force is the charge times electric field, and the magnetic force we know is charge times velocity times the magnetic field. And we see here that charges can be cancelled out, and we have an expression for the electric field. So the electric field is velocity times magnetic field. And the electric field, we know it's constant, and since the electric field is constant, the electric field produced in the conductor is related to the potential difference across the ends of the conductor according to this relationship. The potential difference is equals to electric field times the length of the conductor. And if we put here an expression for the electric field, we have this kind of expression for the potential difference. So, the potential difference between the ends of the conductor is velocity times magnetic field times the length of the conductor. And from the equation, we can deduce that the potential difference exists as long as the conductor moves, because if the conductor is not moving, it means the velocity is zero, and from the equation the potential difference is also zero. Greater speeds and stronger magnetic fields lead to greater potential difference for a given length of a conductor. And if the velocity is reversed, and if the motion is reversed, the polarity of the potential difference is also reversed. We see here minus charge, now it's at the top of the conductor, and the plus charges, now it's at the bottom of the conductor. And if the velocity makes an angle with the wire, and if the velocity and the wire are both perpendicular to the magnetic field as shown in the picture, the potential difference across the wire is found by this expression. And we see here we've just added the function for the sine alpha, and it's because the perpendicular component of the wire is used to find the potential difference. A more interesting situation occurs when the moving conductor is a part of a closed path. Consider a circuit consisting of a conducting bar of length L sliding along two fixed parallel conducting rails as shown in the picture. the potential difference at the ends of a conductor, as electromotive force does, causes electrons to flow in a clockwise direction. And current flows in the direction opposite to the electron flow, so it is anti-clockwise as in the picture. So basically, the moving conductor acts like a battery, and the EMF of the moving conductor is analogous to that between the terminals of a battery. However, the EMF of a battery is produced by chemical reactions, whereas the motional EMF is caused by the external force that moves the rod through the magnetic field. And you see here the scheme of this device. As we said, this conducting rod acts like a battery. And we also can find the equation for EMF by the concept of magnetic flux. Assume the rod of length L, which moves from the initial distance x0 to the final distance x at an interval of time. And because the area enclosed by the circuit at any instant is L times delta x, the flux can be found by this expression. So actually flux is magnetic fields times area, and we said area can be found by multiplying delta x to the length of the conductor, and delta x here is the change in position, x minus x0. And delta x also can be found by multiplying velocity to an interval of time, delta t. And if we put this expression into the equation for the flux, we have a new expression. So the flux is B times L times V times delta t. And we know from Faraday's law of induction that any change in the flux would cause an induced EMF, and it is delta F divided by delta t. Here number of turns is 1. And if we substitute the given for the delta x into the equation, we get delta B times L times V times delta t over delta t. And here it is clear that we can cancel out the delta t at the denominator and the numerator. So we have an expression for the induced voltage at the end of the conductor moving through a magnetic field, but with the minus sign. And the minus sign is no more than a reminder that the induced current is always opposite to the direction of the motion. So we see here, for example, the conductor is moving to the right, and it means that the current here is to the left. Speaking of current, we can find it as follows. The resistance of the circuit, we know it's R, so the magnitude of the induced current is EMF over resistance, or VBL over R. Well, this is the end of the lesson, and if you like our video, please subscribe. Oh, wait. At the beginning of the lesson, we said that induced EMF is the EMF produced by changing magnetic field. However, today in this lesson, you figured out that to induce current, it is not always necessary to change a magnetic field. And that's why I want to make a bit of correction to the definition for the induced EMF. It would be more accurate if we say, instead of changing magnetic field, a changing magnetic flux. So now we can end this lesson. This is the end. Join us and share.